Hello students, welcome back. Lesson 10 is a continuation from lesson 9. We started interval estimation from lesson 9 and we're going to continue on in lesson 10, but there's going to be a fundamental difference between those we did in lesson 9 and those we're going to start from lesson 10. One way to see the difference is through this choice. SE is sigma over square root of n. That's something we used to use, and that goes all the way back to this here. For simple random sample, we have variance of sample distribution of sample mean is sigma squared over n, and taking the square root, we have sigma over square root of n. And also the central limit theorem is based upon this, of course, because the central limit theorem is based upon IID, independent and identical distributed random variables. In short, we need this. But then again, that's a problem. Sigma is unknown. It's population standard deviation, which we don't know in general. We don't even know the population mean, so we are doing this interval estimation for the population mean. How can we say we have a good idea what sigma is? In general, we can't. Now, the second expression makes more sense. Instead of population standard deviation, we are using sample standard deviation S, and that we can measure reasonably accurately from the sample. But then again, the central limit theorem is based upon this. So how can we mend that to accommodate this? Well, that's something we'll have to discuss now. Easiest way to reconcile is for population proportion, binomial proportion. So that's something we're going to start first. And then the next, for population mean, where we have relatively small sample size, we have to do some further adjustment. That's section 3. And then after all those are done, we're going to do a separate new interval estimation for standard deviations. And that's section 4. All right, let's begin section 2. And that begins from the normal approximation theorem that we had been studying since lesson 4, I think. But by lesson 5 and lesson 7, certainly we studied all those. In lesson 7, certainly we did. So for binomial sum, we have this. Binomial average, we have that. Here, P is probability for success, Q is probability for failure, so it's 1 minus P. So replacing Q as 1 minus P, you're going to get this. And that's the binomial approximation theorem. The normal approximation theorem of binomial. So mu is same as P. And sigma is square root of P 1 minus P over n. Or actually, not sigma, SE. SE is square root of P 1 minus P over n. All right. Let's apply this to an example problem. Here we go. In a poll conducted by Harris Interactive of 1,179 video gaming US youngsters, 8.5% displayed behavioral signs that may indicate addiction. Find 95% confidence interval. Okay, all right. So we're doing confidence intervals. So let's begin with a normal picture like this. And then the best point estimate is, of course, 8.5%, so 0.085. And then we want confidence interval here, left-hand side endpoint, right-hand side endpoint, all right? And then as for the probability, to right. 95% of chance that my interval estimate is correct, so it falls into this middle part. And consequently, the other 5% of the time, I'm going to fail. But we have symmetry here, so this is going to be 2.5%. And this is going to be 2.5%. And then, as usual, we have to use end minus center over SE is the z-score. And that's the strategy. Okay, so much for step-by-step strategy. Now let's go to a lot better picture. But this picture has too much information, including the answer. That's why I hid it for a while. So the best point estimate is here, and then 95% in the middle, 2.5% there, 2.5% there. Therefore, we're going to do this. Z-score is going to be end minus center over SE. So left-hand side endpoint minus center is going to be observed proportion, P. And then SE is going to be square root of P1 minus P over N. Let's put some space in between. It's really hard to read. There you go. Nothing is accurate in statistics, so I have to do this. So observed proportion is going to be 0.085. All right. And then how about the standard error? Square root of 0.085. 1 minus of that divided by, what's the sample size? What's n value? 1,179. 1,179, and that has to be associated to the z-score for the left-hand side endpoint, 2.5% here. Remember the z-score? It's gonna be negative 1.96. Let's see. Z-table here. This left-hand side is 2.5%. 2.5% here, and that's associated to negative 1.96. So that's how we get an equation. And solving this equation, that's not too bad. Flip the other side, flip this denominator to the other side, and flip this one to the other side. You're going to get what you want. Here we go. SE computation. And then n minus center over SE is negative 1.96 for the left-hand side, positive 1.96 for the right-hand side. And then you calculate left-hand side, right-hand side. So we have 6.9% to 10.1%. That is my 95% confidence interval. There's about 95% of chance that the real proportion of youngsters displaying behavioral signs of video game addiction, that interval is, I forgot, 6.9% to 10.1%. Yeah, 6.9% to 10.1%, approximately speaking, of course. All right, that was confidence interval. Next, fill in the blank. no less than whatever percent of the youngsters show the sign of game addiction. Find the 99% confidence level. Okay, all right. Answer that with 99%. No less than whatever percent show the sign of game addiction. So no less than whatever percent, but no more than whatever percent. Then, we have confidence interval. Both are out. But we have only one side. No less than whatever percent. So we are looking at something like this. So this is 0.085 as before. And then that's what you're looking for. And there is 99% of chance that I'm right. That leaves me 1% that I'm wrong. I said no less than, but indeed it's less than. So it's this picture we are looking at. N minus center, L minus 8.5% over SC, that will be the same. But Z-score will be associated to 1% here to the left-hand side. Make sense? Let me show you a much better picture. There you go. 95%. So that confidence interval is actually unbounded, one-sided, and 1% there. So if you look up the Z-score for Z equals to N minus center over SC, a bit bigger font, which is lower bound minus center, absolute proportion of 0.085 over square root of P 1 minus P over N. That's my SC formula. And that is approximately equal to L, we want to find out 8.5% or 0.085. And SC is square root of P1 minus P over N, so 0.085, 1 minus of that, over square root of, the sample size of 1179, and that is associated to the Z-score for 1%. If you do it right, you're going to get negative 2.33. Let me show you the Z-score table. Let's see. Standard Z table here. And this left-hand side is 1%. So you look at 1%. Where is it? The closest is right here. And that's associated with negative 2.33. Let's erase these and let's go back. So that's 2.33. Here's an equation. Flip the denominator to the other side. Flip this to the other side. You can solve it for L. And that's what I did here. SC computation, and this is Z computation. Oh, I use a bit better picture, better figure using mathematical estimation. So it's negative 2.326. Negative 2.33 is fine because it came from the Z table I provided you. If you use statistical calculator, you're going to get this kind of figure. Anyway, either way is correct, and you're going to get 6.61% approximately speaking. So that is the 99% lower confidence bound. All right, we went through a confidence interval problem and confidence bound problem. I have yet to consider a sample size problem, but looks like I'd better stop it here and do it in a separate video. So all right, let's resume it next time. in a separate video. I'm out.